Having presented in the second part of the video series the measurement methods VLF, dissipation factor measurement, and partial discharge testing, along with the monitored withstand test, we will now describe the possible fields of application for these various methods. Cable testing and diagnostics are used both on new cable routes before commissioning and on worn cables. Before the commissioning of new cable routes, testing and diagnostics are mainly used to check the assembly quality. Quality defects can be detected on time, thereby avoiding high consequential costs. In addition, newly laid cables are tested for safety-related defects by a simple cable test along with partial discharge testing. A further field of application is testing and diagnostics on worn cables after repair. If a repair of a cable route was necessary, the assembly quality is checked after its completion to establish whether the repair was performed properly and the problem was rectified, or whether there are further faults on the cable route. At the same time, the general condition of the cable route is determined. When evaluating the condition of worn cables, the focus is on checking critical or susceptible cable routes. It is important to understand that the voltage level is deliberately kept low during condition evaluation with cable diagnostics to avoid test loads. Cable testing, however, is only considered when there is a need for this. Diagnostics provides important information that helps to optimize the costs of network planning, as highlighted in Part 1 of the video series. Measurement with a sinusoidal voltage of 0.1 Hz forms the basis for efficient and meaningful cable diagnostics in all fields of application. Since this represents the same voltage shape as that used in actual mains operation, measurement results are provably highly comparable, which is a significant advantage of the VLF 0.1 Hz sine method. Furthermore, the cable route is not exposed to unnecessary loading in comparison to square wave or similar voltage shapes. This is a particularly important and beneficial aspect in the case of worn components. Despite the advantages and disadvantages of each of the different testing and diagnostic methods, such as 50 Hz sine, 0.1 Hz sine, DAC, and 0.1 Hz cosine square wave, the 0.1 Hz voltage shape has the decisive advantage of reproducible and comparable measurement results. This is due to its load independence, which can only be achieved by the true sinus 0.1 Hz sinusoidal voltage. Thanks to the comparability of the measurement results, the operator can build up empirical and reference values in the field of dissipation factor measurement and partial discharge testing. This comparability of diagnostic results massively increases the benefits of cable diagnostics. A further advantage is the fact that the sine 0.1 Hz technology can be used for all meaningful measurement methods, such as dissipation factor measurement and partial discharge testing. Comprehensive cable testing and diagnostics is therefore based upon one unified technology with a 0.1 Hz sinusoidal voltage. Let us take a look at the benefits and significance of the measurement methods based upon 0.1 Hz sine using an example. The condition of a three-phase 11 kV plastic cable is to be assessed with the aid of cable diagnostics. The cable is about 3 kilometers long and has 32 joints within this route. The dissipation factor measurement, performed at the beginning, supplies information on the general condition of the cable. This allows damped joints and joints subject to the tracking effect, water tree aging, or thermal leakage currents to be detected. A high level of accuracy and an overall resolution of 1 by 10⁻⁶ are necessary for the identification of damped joints. In our example, the dissipation factor measurement shows a deviation of the phase 2 from the normal value, which leads to the conclusion that there is moisture in at least one of the joints. The subsequently performed partial discharge testing identifies partial discharges on phase 2 after a length of 669 meters. The partial discharge level of 2000 picocoulomb leads to the conclusion that the cable is in a critical condition, but the results of the partial discharge testing do not necessitate immediate action. Only by overall consideration of the results, together with the dissipation factor measurement, can the condition of the cable be determined. The TDR measurement, which is also used for the location of damped joints, shows that the moisture in joint 4 lies at 672 meters. The fault location identified in the example coincides with that from partial discharge testing. The partial discharge measurement of 2000 picocoulomb is therefore a distorted result caused by the moisture in the joint. The joint is more severely damaged than can be seen from the partial discharge testing and should be replaced immediately to prevent a failure during operation. The subsequently exposed joint exhibits clear traces of partial discharges as well as moisture. The decision to replace the joint immediately was therefore appropriate. To perform measurements like the one described in the example, a VLF sinusoidal voltage source is required, such as Frida TD, Viola TD, or PHG from Baur. With the PDTAT 60 partial discharge diagnostic system and a PC to control it, the measurement of the dissipation factor and partial discharges can be performed in parallel. This is also used as a system in the cable test vans. The PDTAT 60 represents the most compact and lightweight partial discharge measuring device for mobile use on site. This portability makes it possible to perform the measurement directly on the cable, which minimizes interference and thus represents an important precondition for precise and meaningful measurement results. Checking cable routes with the PDTAT 60 is simple, efficient, and precise. It also saves time because the dissipation factor measurement and partial discharge testing are performed in parallel. A comprehensive checking of newly laid or repaired cables, as well as general condition evaluation, can therefore be performed quickly and simply in a single operation, without significant extra expense. This means that the cable only has to be loaded with the test voltage once. To sum up, cable testing and diagnostics with Baur measuring devices can be used for the testing of both new and worn cable routes, whilst adhering to all relevant standards. 0.1 Hz sinusoidal voltage offers optimal preconditions for the use of VLF, dissipation factor measurement, and partial discharge testing, and for the combined variant, the monitored withstand test. The measuring equipment ranges from portable variants to integration in the Transcable or Titran cable test vans. The systems from Baur permit precise and efficient cable testing and diagnostics for fault-free and reliable cable networks. The fourth part of the video series will focus on the implementation of cable diagnostics during operation and the presentation of practical examples.
Baur, ensuring the flow.